Welcome to the Math Record. Today I'll be covering the ICTM Regional 2020 Division AA Freshman Sophomore 8-person, which I'll be splitting into two parts. This video, which I'll cover questions 7 and 11, and then in the next video I'll cover questions 15 and 17. As usual, I'll scroll down all 20 if you want to answer these by yourself. Okay, so that's all 20 questions, and let's begin with number 7. So a circle of radius 5 is inscribed in an equilateral triangle. At each vertex of the equilateral triangle, a circle is inscribed tangent to the two sides of the triangle that meet at that vertex, and also externally tangent to the circular arc closest to that vertex. This process is continued indefinitely. Determine the sum of the circumference of all these circles. So basically, we have an equilateral triangle, and we have a circle that is inscribed inside it. So something like this. Okay. And then basically, what they're saying is that they're making like a circle in here, a circle in here, and a circle in here. And then from those circles, it's gonna keep making more circles. So I'll just draw it. So something like this, a little bit over. Okay, and then another one, right? And this goes on indefinitely. So it makes a one right in the small section like right here, and then even smaller and smaller. And it does that for all three of these corners, right, etc. So we're just going to focus on one because all we need to do is find out the sum of here, multiply by 3 because there's 3 of them. And then you have to add the big one in the middle. And that's all we had to do to find the circumference. So basically, how do we find the radius of each circle? Well, the thing about an equilateral triangle is that if you kind of split this height like right in half, right? And if you put the center of the circle of the big one, so the biggest circle, this point is also called, since it is equilateral triangle, it also coincides with another point, which is called the centroid. And the centroid has a really cool property where the length of this section to this section is 2 to 1. So let's call this entire length L. So if this entire length is L, this would be 2 to 1 ratio. So the total is 2 plus 1 is 3. So this will be 1/3 of the length. And then this will be 2/3 of the length. But remember, this is a circle. So if this is 1/3 of the length, then this section is also 1/3 of the length. That means this section over here, right? This section is equal to 1/3 of the length as well, right? Because 1/3 plus 1/3 plus 1/3 is entire L for the entire length. So now we could do the same thing here, because if we make another triangle and we split it right from the, like there's a tangent line between this big circle and this medium circle, we make this line. This line is parallel with this line, so that tells us that this is 60 degrees, this is 60, and this is 60. So it's another equilateral triangle, and we could apply the same thing. So if we have a dot right here, which is the center of the circle, which is also the centroid of this triangle, then this ratio to this ratio is 2 to 1. So that means this length is 1/3 of the entire length again. So it's just 1/3 of the 1/3. So that is 1/9 L. And this will also be 1/9 L because that's the same radius circle, right? So then this thing will now be 1/9 plus 1/9, which is 2/9. But this is 1/3, which is also equal to 3/9. So 3/9 minus 2/9 is 1/9. So that length is now 1/9 of your length, of your entire length. So you kind of see the pattern. We got 1/3 to 1/9, and since we keep going by 1/3 each time, this is probably going to go to 1/27. So the radius in descending order from the biggest one is 1/3 L, and then the next radius is 1/9 of the length, and then the next radius is probably going to be 1/27 of the length, and so on and so on. So what does this look like? Well, it's an infinite geometric series. So we had to make a summation where x equals, well, we're not going to start at the biggest circle, so we're not going to start here. We're going to start at this one. This is the 1/9. So we're going to have 1/3 times to the power of x, because that's going to be our common ratio because 1/9 times 1/3 is 1/27th, and 1/27 times 1/3 is 1/81th, right, etc. And we start at 1/9. So this has to be 2, x equals 2, because 1/3 squared is 1/9. And then we have to multiply by L because each of them have an L. So that's going to be our radius. So to get our circumference is 2 pi radius, so we have to multiply by another 2 pi. And this goes on for infinity. And remember, these are just one section of the circle. So we need 3 of them, right? So we need to multiply this summation by 3. Okay, so let's just take away the constants that we have, which is L, 2 pi, and 3. So that's 6 pi L times the summation from x equals 2 to infinity of 1/3 x to the power of x. So the formula for an infinite geometric series is just the first term over 1 minus the ratio. So the first term is x equals 2, so that equals 1/9. So 1/9 over 1 minus the ratio. The ratio is 1/3. So that will be 2/3, so 1/9 divided by 2/3 is same thing as multiplying by 3 over 2. So that is going to be 1/6. So 1/6, and then so we have 6 pi L times 1/6 is equal to pi L. So that means the sum of the circles for all 3 of those vertices when we keep making those circles, right, etc., is going to be pi times L. That's the sum. So let's just put that down first. And then what's the circumference of this circle? Well, 1/3 pi L, which is our radius, times 2 pi. So it's going to be plus, because you have to add the middle circle, which is 2 thirds pi L. Okay, so we got that. So we got the entire thing. Now we just need to find the length of this entire height. So how do we find that? Well, basically, let's just delete all of this because we technically don't need it anymore. We just need to find the length. Well, we know that it's the circle that's the biggest is radius 5 because that's what's given in the question. So if we have an equilateral triangle, right? I'm just gonna draw a general picture. And this is radius 5, right? And this is 5. Remember I said that this is 1/3 of the length, right? And this is also 1/3 of the length, right? And then this is also 1/3 of the length when I made the height. Then since this is just 1/3, we just need to multiply by 3 to get entire length, which is 15. So our L is equal to 15, and that's basically it. Now we just plug it in. So then pi times 15, so 15 pi, plus 15 divided by 3 is 5. 5 times 2 is 10, so 10 pi. So add them together, that's 20 pi. And that is your answer for number 7. Okay, now let's begin with number 11. Let's go to number 11. So in the diagram, AE to EB is 3 over 5, BD over DC is 1/2, and they intersect the F, and the numerical area of this big triangle ABC is 1,824. Determine the area of this quadrilateral BEFD. Okay, so let's kind of draw how this looks. So we have some kind of, then something like this. So I'm just drawing a general picture. It doesn't have to be that precise. So I'm gonna draw a line from here to here, then from here to here, and then one final line, I'm gonna go from this vertex to this vertex. Because there is something called Seva's theorem, which we had to use for concurrencies. Concurrencies, not congruencies. Basically, they all intersect at one point. That's called concurrency. So they say AE is 3, and then they say EB is 5. Well, the ratio is 3 to 5. That's not exactly their length. And then BD is 1, and DC is 2. So Seva's theorem basically tells us that um, basically this side length divided by this side length, and then this side length divided by this side length, and then this side length divided by this side length, multiply those 3 numbers, and it should come out as 1. So that's Seva's theorem. So 3 over 5 times 1 over 2 times, let's call this A and this is B, times A over B is equal to 1. So this is equal to 3 over 10 times A over B is equal to 1, right? I kind of didn't leave space, but basically this side is 3A over 10B equals 1. So A is probably going to be 10 and B is equal to 3. You just use the least common, it doesn't matter. So A equals 10 and B equals 3. Okay, so now we have that. So what we're gonna do now is we're gonna use something called mass points. So if you want to find this vertex and this vertex and this vertex, all you have to do is look at the opposite side. So for this one, you gotta look at these two. For this one, you gotta look at these two. And for this one, you're gonna look at these two. So basically, it's pretty simple. All we have to do is look for least common multiples. So what's the least common multiple of 10 and 5? Well, that's 10, so it's 10 here. What's the least common multiple of 3 and 2? That's 6, so that's 6 here. What's the least common multiple of 3 and 1? Well, that's 3 here. And then now we have to find these points, which is also pretty simple. We just add the vertices from both ends. So 10 plus 3 is 13. 10 plus 6 is 16. 9 plus 3 is, 3 plus 6 is 9. So basically, now we could do the same thing here. So we have this line. So this is 13 to 6, so you got to invert it. So 13, 6 here and 13 here. And then same here. So this is 9, and then this will be 10. And same thing for this line, which you have to balance, which is 16 and 3. So basically, how do we find the area of our quadrilateral, which is this section? Well, basically, we know that the ratio between this triangle to this triangle is 3 to 5. So that means the area of just this triangle is 5, and then 3 plus 5 is 8. So it'll be 5/8 the entire area. Okay, so now if we look at this triangle and we basically kind of tilt our head, we can see this triangle and we see that triangle. So out of that 5/8 triangle, we know that 3 and then 16, which is 16 plus 3 is 19, so times 19. And then 3 out of 19 is equal to this triangle. And now we just need to find this triangle. So basically, we look at this triangle, which is 5/8. Remember, 5/8. And then multiply by 16 over 19. So we're just working with ratios right now. And then from that 16 over 19 triangle, we need to get this area. So if we kind of take our head again for this one, we see this side length and this side length. So 1 plus 2 is 3. So 1/3, because this is 1, so 1/3 of the entire area will give us this area. So if we add those two, this area is this ratio. This is the ratio of the total area for this area. And this area, this ratio is the total ratio for the area for this. So basically, we have these two, so let's just kind of add them together. So I'm just going to multiply this one by 3 over 3 because there's a 3 on the bottom. So this is 9 times 5, which is 45, plus 9 times 16, which is 80. So 80 plus 45 is 125. And I'm just going to leave 8, 19, and 3 on the bottom because we're going to have to multiply by 128 to get our total area for the quadrilateral. So let's divide by 8 first because it seems like actually let's divide by 3 first because it seems like the easiest. So this is 608. And then let's divide by 8, which give us 7. So that's 56. So that's 48. 48 divided by 8 is 6. And then divide by 19. So that's 38 and 4. So this simplifies to 4. So 125 times 4 is equal to 500. And that is your answer for number 11. And that's basically all you have to do. You have to use Seve's theorem, use mass points, and then basically finding ratios between these triangles. Well, thanks for watching, and I'll see you at the next part of this video. This contest. And here are all the answers.